Today, we're diving into a really fundamental problem in computing. How do you stop a super powerful search algorithm from just giving up before it finds the actual best answer? It's a question that, believe it or not, has a huge impact on everything from engineering to medicine.
Think about it. From designing the perfect curve of a jet wing to discovering the next life-saving drug, computers are constantly wading through problems with trillions upon trillions of possible answers. So, how in the world do they find that one single best solution in what's basically an infinite haystack?
Well, the answer is actually kind of cool and organic. Computers often use something called evolutionary algorithms, which pretty much mimic the process of natural selection. But these amazing tools have a massive weakness. They have a really bad habit of getting stuck.
To really get what's going on, we need a good analogy. So let's reframe this whole complex computer problem as a massive real-world expedition.
Okay, picture this. You're dropped into a gigantic mountain range you've never seen before, and the whole thing is blanketed in a thick fog. Your one job is to find the absolute highest point, the true summit. You can't see a map. All you can do is feel the ground beneath your feet. Where would you even start?
Well, for starters, you probably wouldn't go alone, right? The standard way computers tackle this is by sending out lots of teams of explorers to cover more ground way faster.
In the world of computer science, this approach is called a shuffled algorithm. That population of potential solutions is just our huge group of hikers, and they're split up into smaller teams to explore different parts of the mountain range all at the same time.
And this is the basic strategy. You see the teams go out and explore their own little areas. Then, every so often, they shuffle. They all get back together, share notes on who's found the highest ground, and then they head back out. It's this constant cycle of searching and sharing.
But here's the catch. This whole strategy has a major vulnerability. There's a kind of trap hidden out there in the fog, and it gets almost every team, every single time.
Now, the technical term for this trap is premature convergence. But that's really just a super fancy way of saying the algorithm gets overconfident and declares victory way too early. It settles for a pretty good answer instead of hunting for the best answer.
So here's how the trap works. The teams find what's called a local optimum, a nice high foothill, and they plant their flag, thinking they've made it to the top. But the real summit, the global optimum, is still way out there, totally hidden by the fog. They've been tricked by a false peak.
So why do they all fall for it? Well, it's basically groupthink. If every single team is trained with the exact same technique like only climb straight up, and they all start in roughly the same area, they're all going to march up the slope to the exact same foothill. There's no diversity in their strategy.
This is where things get really interesting. A group of scientists developed a new, much cleverer algorithm that's specifically designed to avoid this exact trap.
It's called the Shuffled Multi-Evolutionary Algorithm with Linear Population Size Reduction. Yeah, it's a mouthful. We'll just call it L-SMEA. But that long name actually tells you its two-part secret weapon. It uses multiple strategies, and it shrinks its search teams over time.
So first, it completely blows up that groupthink problem. Instead of everyone using one rigid climbing technique, L-SMEA gives each team a whole playbook of different search strategies. So at each stage, the teams switch up their approach. This diversity is baked right in, which means they're not all going to follow the same path and get stuck on the same old foothill.
The second part is all about smart resource management. This is the linear population size reduction bit. L-SMEA starts out with a ton of teams to explore the entire mountain range, casting a really wide net. But as the search continues, it starts to see which areas are promising, so it smartly recalls the teams that are stuck down in low valleys and sends their resources to back up the teams that are getting close to the really high peaks. It's this brilliant shift from a broad search to a razor-sharp, focused final climb. Okay, so the theory sounds amazing, but does it actually work in practice? The researchers decided to find out by putting L-SMEA head-to-head against the older single-strategy algorithms.
And let me tell you, the results weren't even a little bit close. In a big, standardized test against two of the classic methods, L-SMEA just dominated. You can see the win counts for yourself. It was an absolute landslide.
But get this. This is the most incredible result of all. When they pit it against another major algorithm on 30 different, really complex problems, L-SMEA won every single time. A perfect 30-0 shutout. It just didn't get stuck.
The research's own conclusion really says it all. That combination of having a playbook of different strategies
and smartly focusing the search over time, it just creates an algorithm that's way more effective and way more robust. It's literally built to avoid the trap.
So an algorithm that's better at climbing virtual mountains, that's a neat computer science trick. But why should we care? What does this actually mean for the rest of us?
Well, these kinds of optimization algorithms are the hidden engines that are driving progress in, well, almost everything. They're being used right now to design more efficient airplanes, to build smarter economic models, and to speed up all kinds of scientific discovery. When optimization gets better, everything gets better.
And that's really the bottom line here. Every time an older algorithm gets stuck on one of those local peaks, it means we end up with a slightly less efficient engine, or a financial model that misses a huge opportunity. Finding the true summit isn't just a win for the algorithm, it translates directly into real-world progress for all of us.
And that kind of brings us to a final bigger question. The biggest challenges we face as a society are, in a way, just massive optimization problems. So if we can teach our computers how to search smarter, to be more resilient, and to not just settle for good enough, what new summits could we reach? What problems that seem impossible today might just be one smarter search away from a solution?